I'll pass a for everything. I'm taking this solo night, so it'll be easy for you to understand things. Huh? A current I, this will be I, and this current I will set up an external field that is B naught. And what is that B naught? Mu naught Ni. And we know from definition mu naught H. And what is H? H is Ni. How to vary H? By varying current, because we don't go for N. What is N? Again, N is N by L. Number of turns per unit length. And what is L? L is this one. In books, they didn't give much description. Students will think H is some sort of, no, in a solenoid, just vary current, the H will vary. What is capital H? Magnetizing field intensity. What is B naught? Magnetizing field. How much B naught is what? H. The measure of B naught is what? H. Able to understand? Yesterday, I think we gave some description about all these quantities. So how to vary the field? By varying H. This one. And what is the next? This one. So this particular, in what direction the induced magnetic field will be set up? In the direction of B naught, because there is a ferromagnetic rod. So Bi will be very much greater than B naught. This what overall the ferromagnetic substance, it will take place here. So I'm interested now. Let me vary H. I'll increase H, because earlier this iron rod is not at all magnetized. Okay, let me magnetize it. I'll vary H, I'll increase H, then I'll decrease, then we'll see what conditions will come. So this called like nothing but the hysteresis curve we are going to discuss here now. Now let me vary the, so as I increase H, so first it will start from 0. It will increase. So as H increases, the B will increase. What do you mean by B? The net field, what is B? Some books, they have wrote this as intensity of magnetization. I think nothing wrong. In y-axis, they took intensity of magnetization, nothing wrong, because what is the total magnetic field? How much a substance got magnetized, that's what intensity of magnetization. How much of net magnetic field depends on what? How much the substance got magnetized. And for ferromagnetic, the Bi is very much greater than B naught. Even in place of B, some books they given high intensity of magnetization along y-axis. The curve will be same. So don't get confused here. Everything will be same, that one. So as I increase the current I, the B naught will increase. Then you go back to the domains. So usually what is the ferromagnetic substance? The domain will be there. So the net magnetic field initially will be 0, Bi. So as I increase the B naught, then one of the domain will force the other domains to align their dipole moment in the direction of B naught. And as the net dipole moment increases, the Bi will increase. So therefore this will increase here. And finally what will happen? We will get a curve like this. And as I further increase, there won't be further change. You can see that one. It got saturated. Even increase H, or the B will remain constant. This is called a saturation. Why do this saturation? When all the domains get aligned, tell me what will be left over there. There no more further any alignment will occur, no? Then the ferromagnet says that S, I'm saturated, no more further alignment, because if all the domains, in all the domains, if the dipole moment of all the atoms, if they are in the direction of applied field, finish, or no more further alignment will occur, and it gets saturated here. So no more further induced magnetic field will increase. That's why in the books they took that as y-axis intensity of magnetization. And this bi will be several thousand times. Bi will be several times, thousand times of b naught. Okay, it means you can put, don't think in this way like, sir, h increases, b naught will increase, b naught increases, bi constant, b will increase. So y horizontal curve, bi will be several thousand times. So therefore, even the small change in b naught will not help much. So it will get saturated here. So now these are the some points. We'll write it. This is O, this is A, this is B. Next, after this, when I start decreasing, I'll decrease the H. How to decrease H? By decreasing current. So as you decrease current here, so what do we expect? We expect that the BI should also decrease, no? But it will not follow the curve. So initially what happened? It was following. You can see this. It was following like this. So when we decrease the thing, no, so I'll till here will, now it will be that one. So when HS, when current through the solenoid has become zero, we do get some magnetic field still left over. So what does it mean? The substance got magnetized. It has retained some magnetization. So it will not retrace path. It will not retrace path. We'll get like this curve. Are you able to understand? If it were O, A, B, B, A, O, if it were come like this, means once you make current zero, then no longer this will behave like a magnet. But here what happened? You keep on increase current, this will get magnetized as long as current is flowing. Then once you again decrease the current, then what do we expect? As some induced magnetic field will decrease. Once current becomes zero, what we thought is like Bi will be zero. No, it will retain some magnetization. What happens is the domains what all will not come to their initial state. They will retain some dipole moment. The substance will retain some dipole moment. It got magnetized. It got magnetized. So shall I say retentivity, residual magnetism. You just wait. Let me finish off the total this one. So this called like a R, OR. I'll give you the symbol R. What is R? OR is called as a retentivity or residual magnetism. OR is called as residual magnetism. I'll show the domains later on. First, let me explain the curve. It'll be easier that one. So once I become zero, H becomes zero, still it will retain some magnetism. Then what I do is I will change the direction of H. How to change the direction of H? Change the direction of current. So I can also do like this, no? Current was, yeah, like this. Now the B naught direction will be in this direction. BI, let me show it time being like this. No. As I change the direction of current, how to change the H? By just changing the direction of current through the solenoid. Is it very easy? Yes, it's quite very easy. There's a battery is there, variable EMF, that one. I'll change the polarity, the current direction will change it. Then as H now, H becomes negative. So what it will do? It will now what happen? Induce magnetic field opposite to the earlier induction. Earlier there was a magnetism. Then what happen? The B naught is there. So some of the domains what happen will align itself in the direction of B naught. They will force other domains which are having magnetic moment opposite to the initial one. So gradually what happen at one point, so what happen again, the net magnetism inside the metal will become zero. The net magnetization has become zero. So this is called like a coercivity. So what is OR? OR is called as retentivity, residual, retains, and OC is called as coercivity. Coercivity, coerce. Now, any government that is working for welfare of government, but nowadays the opposition parties are coercing their plans, or they're coercing their particular the motives. Coercing means what? Opposing that one. Coerce force, COERCES. The grammatical meaning that one. Coerce means one which will be opposition. So coercivity, what it will do? It will eliminate. Means residual that one. Means here the value of H at which what will happen? The total magnetism inside the material will be eliminated, coerced. So there was some magnetism left over, no? That everything what happen will get eliminated here. So at this particular point, what is the magnetization substance? Zero. You can see that one. Here zero. Again, the substance will get back to the original state. Then as I further increase H, then the magnetization will come in opposite direction, the BI. And again, the what happened? The domains will start aligning. Again, when all the domains they get aligned, no saturation will be attained, and further increase in H will not make further alignment of domains. So this is saturation. So now again I'll decrease H. Then again the curve what will happen will take a shape like this. Then when H has become zero, it will still retain some like a magnetization. That's called like a retentivity again. So again, I'll change the direction of H. So somewhere at this particular point, it will become zero. The total magnetization is zero. So again, if I increase, it come like this. So you see, it's not going to. There's a one cycle. There's everything will become one cycle. O C D E F B. This will become one cycle. So when I go round like this, means I'll start from here. As the magnetizing field intensity increases, the magnetization increases, or magnetic field net magnetic field strength increases. The domain starts getting aligned. They'll get saturated. Further increase in H will not increase the magnetization. Then, if I decrease H, it will start decreasing. Then at one point, when magnetizing field intensity is zero, it will retain some magnetization. But the substance got magnetized. If you remove this particular ferromagnetic rod here in this position, no, it got magnetized. But iron is not a magnet, but we can magnetize it. This is called like an artificial magnetism. How to produce artificial magnets? By this method. Or I told you earlier yesterday one method. What is the method? You just hammer it. Tell me for how long years you have to hammer? 10, 15 years. Look at this pass current. Within 1 hour, what you'll get a powerful magnet. How much powerful you want, you'll get that much of powerful. Like that in applications, we need very powerful magnets. So where do we use? Particle accelerator, the nuclear bomb, almost all the, especially the nuclear technology, we need particle accelerators. There we need high powerful magnets, superconductors, there we need. Most of the applications, we need this one. High magnetic field is needed. How to produce that? For that, we need powerful magnets here. That to open, size should be small. Everything is obtained here. Tell me, where is the 15 years to produce a very good magnet, powerful magnet, and where is the 1 hour? This was the science and technology. Huh? If you are good in science and technology, the nation will be powerful. America, why superpower? Not because of the technology, it's just because of technology. They know how to use science and technology. They are powerful, finish over. They know how to use resources. Germany, Japan, Russia, Italy. Why not India? India, China, Pakistan. What is the problem? We are not utilizing science and technology. Got it? There's a clear-cut message. Huh? You want to become superpower? Yes. We need a students who really think, who do research, who will find out the new things, and will start using resources in a very systematic way, very productive way. The nation will become superpower. The lack of intellectuals in India, I should say like that. If you want to check in Google, you have an exact description. what made us. Maybe it may take another 200 years to catch Europeans. We are in that state. Still, we have to far lagging behind. Slowly now we entered into bookish world. It may take another 50 years for us to digest bookish world, then practical world. From practical world again to research world. Then from research world to manufacturing world. Then comes that one. So it happened. So in the Europe, what happened? It started from 14th century. Our science started from 19th century. So within 100 years, not possible to change society so rapidly. To some extent, we have made progress. So it may take another 200 years for us to come to a one particular state, that one. So how well systematically we design our education, things that matters a lot. So it's a responsibility of you now. As a teacher, okay, what I know, I'm sharing it. But as a student, now what happens? You have to grow. You have huge responsibility on you to carry forward this nation. How good thinker you are, not just solving numericals, practical approach, practical analysis, manufacturing of it without any defects, productivity, efficiency, all it matters. It's not that easy. For that, you need sacrifice. If you watch Big Boss, for every weekly 3 movies, then IPL cricket is there, then that. You are in enjoyment world. How you are unable to sacrifice? Okay, per day entertainment, half an hour I think sufficient. For a human beings, half an hour is sufficient. For half an hour you listen song or you watch something, or 1 hour you put it. But the remaining other time you should spend. But we have a totally different mindset. We think that enjoyment is what everything. There makes a lot of difference. When you spend 4 5 hours watching TV, how it is possible? Not only you, I'm not talking about you, in general public here. 4 5 hours per day they sit in front of TV. How it is possible? How do they can concentrate? This is what happens in research labs, no? The one person comes home, hardly will take pen paper and study something. Only in office he'll do research. Not possible. I think some of your parents or relatives who are working in defense lab now do make observation their lifestyle. Will not help that lifestyle. It's my teacher, my responsibility to enlighten you. Afterwards, left to you which particular path you want to pick up, enjoyment life or thinking life where you want to do something for nation. It's left to you. Okay, this is about the history. So finally, I'll come back to the original point. This one I started. So this is one cycle. No? What is the one cycle? You have to take it from here. B, R, C, D, E, F, B. This is one cycle. So what I see is that there is some heat will be generated. For that, I should do work, no? To make it to undergo variation. Sir, why you are doing work? See, to send a current, somebody should do work. What is that? The cell does work here. The current H should increase, then decrease, again change direction, again increase, decrease. The cell does work. What all the energy is supplied by cell? Where do it has gone? It started from here, it is here only. Then I go and calculate the energy that one. So that energy will be lost as heat in the material. So the hysteresis curve becomes very important. The area under the curve, what happens will help us to differentiate the different types of materials, classify the materials. So the area of BH cycle here, the area under the curve, what happened? It is equal to heat dissipated in one cycle. So what is this area? Why do that heat dissipated in one cycle? Where do that heat dissipated? In the material. Heat dissipated in the material. Let me write that also. In the material means this rod itself, in the material, in one cycle. So depending upon the applications, I'll pick up the elements, I'll pick up the like a material where the area of cross section is more or where this area is more less. What happened based on that I'll pick up here. So this called like a hysteresis loop. The name of the topic will give name for this hysteresis. Hysteresis. Hysteresis means hysteresis. What is the meaning of lagging? You see that the B lacks H, no? Suppose say like a year, H increases, of course, B will increase. Afterwards, H increases, B will not increase. As H decreases, the B will not decrease. So B is lagging. The B lags behind the H at all points. Now H is non-zero. What is B? B is zero. H is zero. B is certain, should be zero, no? But it's reaching value. So at all points, what happened? The B lacks H. That lagging word is called as a hysteresis. According to the Greek or the Latin, the lagging word is called as a hysteresis. Hysteresis. So that we call hysteresis, that one. So B lacks H. What happens here? Altogether, well, I think course it I define, no? Okay, no. B lacks. That's why called as a hysteresis in that one. Okay, now let's come for that particular the domains at O. How the domains will be? I think I'll try to draw here only. Let me assume that one here, and at A, nearby diagram needs space, no? At A, I'll show the domains. I think a little bit some help will come, so it will start getting aligned. This is initially zero, no? Some rough diagram, and at B, what will happen? All the domains, I'm not showing the shape of the domains, rough diagram. It got aligned, finish over. Further you increase, it cannot change. Finish over. There's the upper limit for that particular domain. Again, at this particular point, and here if you commit, there's a net dipole moment, R, at R this is. If you check the substance, there's a net dipole moment. Fine. Here net dipole moment at O will be zero. Able to get this? So when it comes here, again you check it now. So finally at C, what is the state of at C? It should be the same thing. Huh? At D, what should be the diagram? You have to show everything getting aligned here. At B, again at E, one last diagram. It should be opposite of this condition, what we have. And it will be somewhere here. Got this? So it's a maximum. The mnet will be maximum. You see what's happening to here? The domains, they are made to rotate, no? The atom, they're made to rotate. So to align the domains, what happens? There'll be friction between the domains or between the atoms, that one. So some work has to be done. Some energy is needed to align the domains. That energy, what happen, will get converted into heat. There's a reason why heat is dissipated. So why that heat is dissipated? To align the domains, what happen? Energy is needed, or the friction will be there. Due to that, what happen? And heat will be generated. So there's a main cause for why the heat will be generated in hysteresis loop. There's the simplest idea. How to change that H, I think you got it. Of all very important, I'm more interested in what, like the area under the curve, this length OR and this OC. Okay, now I want a very good artificial powerful magnet. Tell me what I should do. I should pick up OR very large, no? Means what I should do, I'll bring that particular, I'll wound a wire on it. Clear this, I'll pass a current, I'll increase the current, then the curve will take place like this. Fine. So then I'll keep on increase H, get saturated. I'll decrease H, I'll decrease current, I'll make current I 0. Once current I 0, then what happen? I will take out this wire which is wound on solenoid. Then I'll remove that particular rod from the solenoid, and that is what now a permanent magnet here. It has become a magnet. Finish over. Will it retain forever? It's as long as that it will retain. So now this has become a magnet. The substance has become magnet. Artificial magnet here. So who can undergo this magnetization? The ferromagnetic substance, not dia or para. We have already seen they're having less magnetization. So iron, cobalt, nickel, steel. These are the very four elements are there. Then next alloys, which I prefer here. Okay, got this. I think the value of OR and OC is what something very crucial for us. So based on that, I can classify the ferromagnetic materials which I use for applications. Agreed, all of you? Shall I come out of this? These domains, they may ask you diagrams like this also. So this is the permanent magnet. Now here is what permanent magnet is obtained here. Okay, let's get into the application part. So this hysteresis curve based on this. And now if I plot the hysteresis for soft iron and steel, for the soft iron, the area is less. You can see very much from this. Good questions can be asked, just information based. Look at the area green color. It is definitely more than this particular thing. S.C. Verma, he has shown it separately like this. In some of the books, they have overlapped so that the students can analyze here. Now, when I compare the steel and soft iron, no, I do have the areas like this here. They don't have different material, they'll have different value of the, and high, nothing, no problem. I already told you what is high. Intensity of magnetization. Okay, but here I'm showing B. So don't get confused here because the net field inside the material is nothing but what? The measure of intensity of magnetization, how much the substance got magnetized, that is what I know. And the measure of I is nothing but the net field inside the substance. So both are same. So don't get confused. That's why I brought two diagrams so that will be easy for you. Okay, no, this what you're showing. So definitely the iron is having less area than steel. Agree this? Okay, let's come for that one. Now retentivity of soft iron is greater than. So if you look at this, some data what is available. Retentivity of soft iron is greater than that retentivity of steel. This is one information. Coercivity of soft iron is less than the coercivity of steel. The coercivity means this is the retentivity R1, C1, R2, C2. Coercivity of which one is more? That of the steel is more. And retentivity of which one is more? Soft iron is greater than that of retentivity of steel. Some one of the book they given data. So from this, what we can write here, OR2. I'm comparing both the diagrams. Retentivity of soft iron is greater than OR2 greater than OR1. The coercivity of steel is more than that one. OC1 greater than OC2. I think this data is very important. Next, area of hysteresis flow of soft iron is much smaller than that of steel, so that hysteresis loss per unit volume per cycle is less for soft iron than steel. Area under the curve. Next, again, the permeability. Mu R. Mu R for which one will be more? For iron, it will be more. I think I'll check the data. think I lost it somewhere. No, the relative permeability. What is this steel actually? Steel, what it is made up of? It's an alloy, no? Steel is an alloy. So I'm just going for a good comparison of this steel and iron because that is what we widely use here. No, I'll write all the data. Next, permeability, no? Mu r is greater for soft iron. This is steel. Susceptibility of iron is greater than, I think we need all this data, retentivity, coercivity, hysteresis loss, and all this one. There's a 1, 2 like this, and there's a 3, the data. Coercivity, there's a 4. And the area. Okay, this data you have to remember here. Okay, let's come for this. So I have this much of information. Now I'll come for this one. For are greater for soft iron than for steel. Permeability, susceptibility, retentivity are greater for soft iron than for steel, are less for soft iron than for steel. Like this, we'll categorize, we'll keep it. Okay, now let's come for the first application, permanent magnets. What is the basic feature of permanent magnets? What all it should have? Say all this is theoretical information just to go through one syllable. It should have high retentivity so that it produces strong magnetic field. You should have high coercivity so that its magnetization is not destroyed by stray magnetic fields. What do you mean by stray? Minor mechanical damage. Suppose you take bar magnet. This one. What is it? Not natural, it's artificial. I just wound a wire on it. I'll pass a current. I'll make it to undergo the path O, A, B, then C. Then it'll get magnetized. Then I'll take it out the solenoid wire. Then it got a magnet here. Then there'll be stray magnetic fields. No, stray magnetic fields means like if it is nearby a current carrying wire, it got magnetized. It's having a dipole moment. This particular current carrying wire nearby it can produce a magnetic field. No, and if this produces magnetic field in such a way, it should produce. Oh, no. Let's assume something here. Okay, it produce magnetic field in such a way that uh, some. Okay, well, there's a body. I'll put it. There is some current carrying structure. Current carrying body it is. If it produces magnetic field such that the magnetic field is in this direction. Tell me what point to resultant dipole moment. Now what is this M? By hysteresis loop, I made it magnetized. And what is this Mi? Due to this particular body. This is what I'm using in some application. This is magnet produced. I'm using in application. There are some surrounding objects are there where they're carrying current and they'll produce magnetic field. And because of that, dipole moment in the magnet will be in this direction. Or say like some B external. Same thing. They're the external, no? Now what this B external will do? Will try to decrease dipole moment, no? And if the B external is such that if it can nullify this, how much struggle you made to produce this magnet, artificial magnet, no? That everything what happened, it get demagnetized. So therefore, what I should take care now? For a permanent magnet, what should be given priority? The coercivity should be given priority. Even if it's having less retentivity, if it's having high coercivity, means once you say what is the problem is, suppose that let's go to some microwave oven. There's a magnet is needed. I manufactured a magnet, artificial magnet. I fitted inside that one. Due to some other elements, current carrying elements, it will produce a magnetic field. And the magnet which was fitted in microwave oven, okay, what happened? It gets demagnetized, finish over. It will lose all magnet. Why? Because of the stray magnets. Then what happened? Again, what you should do? You should come, open the microwave oven, open the part where this artificial magnet was introduced. Then again you magnetize it, remagnetize it. Again you have to introduce. It may cost you some 2,000 rupees. Cost of oven 10,000 rupees. It's a big problem, no? So once a magnet kept inside any equipment, I should not remove. Example, loudspeaker. I should not remove. In television, we have magnet. Everywhere in equipment, what happen? A artificial magnetism is needed. So once it is fitted in the equipment, it should not be removed. It will be very costly. It will be big trouble. So at any cost, I should see that it should not get demagnetized. So therefore, what is the priority now? For a permanent magnet, the coercivity should be very high, though let it be less. So then one more thing, permeability should be high. If it is a very good permeability, yes, good magnetization will be obtained. Powerful magnet it will become. So then therefore you see that one. High retentivity is needed, high coercivity, high permeability. Still what will happen? I'll prefer soft iron only. In spite of its slightly smaller than soft iron, steel is favored for making permanent magnets. The reason for that? What is the reason for that? Which is having more retentivity? OC1, steel is having more retentivity than the iron, no? But you look at the retentivity of, like a coercivity of steel is more, but retentivity of what? Iron is more. So I want artificial magnet. Shall I pick up iron or steel? Though the retentivity of iron is more, but still the steel is preferred because they're having more coercivity. What is the reason for that? Because the permanent magnets, what happens once you magnetize it, at any cost, it should not get demagnetized. So that's why, in spite of its slightly small retentivity than soft iron, steel is favored for making permanent magnets. Steel has much higher coercivity than soft iron. The maintenance steel is not easily destroyed by stray fields. Once magnetized under a strong field, it retains it for a long duration. Getting the idea? So I told you high retentivity, but the high coercivity is given priority over high retentivity. High permeability as iron and steel. Almost they're having, because what is the steel? Again, it's a alloy of iron only, no? So steel, what happened? So there's a composition: iron, cobalt, chromium, magnesium, carbon. If I mix up cobalt steel, carbon steel, so these are things. So these are the different types of steels are there. Which I'll prefer that one: cobalt steel, carbon steel. Okay, got this. Permanent magnets, what means steel is preferred. Is it okay? Conclusion. So I think I have to shade it here. Steel is favored for making permanent magnets. This is the thing. Because of its high coercivity. There's everything, especially there in SU Verma, he has given in paragraph, not summarized here. So that if you get a lot of confusion. This I picked up a paragraph where clearly he has given all the reasons. Okay, let's come for that one. Electromagnets. So for electromagnets, what is the type of? High initial permittivity, low retentivity is needed. Means what is electromagnet? As long as current is flowing, it should behave like a magnet. That's all. No. Once current is zero, it should not get magnetized. It should not retain any magnetism. Where do we use? Where do we use loudspeaker? Many applications are there. Electromagnet is having wide applications. Means as long as current can you hear me?
Yes, sir.
You may some power gone with mobile data will run. Will manage. Oh, oh. Yeah. Shall I continue?
Yes, sir.
Shall I continue? Okay, fine now. Now, for electromagnet, what is the basic necessity of electromagnet is once current, when you're using it should behave like a magnet, the material. Once you stop using it, it should not be. Means when current is flowing, it should behave like a magnet. Once current through it is zero, it should not behave like a magnet here. So for that, what happened? It should not retain any magnetization, no? So low retentivity. I think this is the idea. Magnetization is lost and the magnetic current is switched off. Means as long as current flowing, it should behave like a magnet. Once current zero, it should not be magnet. So better let it have low retentivity. Soft iron is more suitable than steel for cores of electromagnets. This is a thing. There's a requirement for electromagnets. Got it? Now, transformer cores. I think already we discussed core transformer. Can you remember? I think I'll take you to the diagram. These are all theoretical. Please just read and come to conclusion. You'll be on safer side. No, nothing big, no. Okay, can you remember this is a primary, this is secondary, and this is a core, no. And that what pen it was laminate. It was retentivity of which one is more. OR2. OR2 is less than OR2 is greater than OR, no? Okay, okay. I think some data. I think some it should be steel. Huh? I think I'll go for steel. That one. Electromagnets, no? Iron is having more retentivity, permeability, so that magnetization is large even for a small magnetizing field. I think I should give priority for permeability here. Huh? Permeability is what given priority. Yeah? Not this one. I'll low retentivity. Permeability is given priority. Huh? Based on this, the electromagnets are picked up here. Okay, I just change it. So rather than this should be given priority for electromagnet. Anyway, like the retentivity again will go for the iron, no? Though it's a steel, no? Compared to steel, it's having high permeability. Okay, now last one, transformer core. So if you remember, there'll be some eddy currents will be there, no? So if you can laminated core. The core will be laminated, no? So here what we do, we don't permit the eddy currents to complete the loop. Can you remember this? So what is the best thing is like you take a paper, cut it like this. Then like this, similar some thousand papers, thin papers you stick on. I think you'll get some thick square frame where this will be our notebook. I think best thing is notebook, the pages where the eddy currents open are not permitted. So what is the method? First you take thin iron frame. Okay, that one. Here you apply insulating material. Then you place another iron frame on it. Then place another iron frame. Like that between the iron frames. Here open an insulating layer will be there. That insulating layer will not permit the eddy currents to complete the loop. Like that what happen? By laminating the core, what happen? We can minimize the losses due to eddy current. Okay, that's come for this. Next again. Now here what happen? Inside this particular thing, how the current will vary like this. No, the voltage you can see. So the current is constant or variable in transformer. It's variable, no? So we do get current here like this, and it will change direction also. So one cycle what pen it will undergo hysteresis. So tell me like what is the state condition that one? This particular material which I'm using for the core of a transformer should be have more area in hysteresis loop or less area? Less area. So which is having less area? Iron. As materials are subjected to alternating magnetizing fields of high frequency. Are you getting now? Look at the AC signal. It will increase, then decreases, then changes direction, increase or decrease. Similar to hysteresis, no? So therefore, the BH curve, what I'll get it here, it should have minimum area. Because here H increases, then decreases. H changes direction, increases, then decreases. So exactly one cycle As the AC signal completes one cycle, the BH curve also will complete one cycle. So what should be the electric field? Having less area. So therefore, the core of a transformer should be made up of iron to avoid, to minimize hysteresis losses. Low resistivity. So this particular current, what happened here, the resistance losses should be minimized here. Soft iron is preferred for making transformer cores and telephone diaphragms. Okay, this equipment we don't know, just leave it here. High initial permeability. Why? Because more flux will link. No. So of all the transformer, this is given the priority. I'm just shading that particular thing. So therefore, the core of transformer is made up of the iron because the hysteresis losses in iron is less compared to the steel. Okay, got this permanent magnet, electromagnet, and the hysteresis losses and transformer cores. The area under BH curve will become heat generated per unit volume per second. That one, the total heat generated, B into H. There's a very good theoretical questions can be asked. Just do remember this one. One apparent dip is left over. Tomorrow I'll cover in the numerical session. I'll start the optical instruments. Now I think I picked up some everything. So in the form of a curve is what is showing us some very good diagram. And now you see why they're given so much of importance. The magnetic memory is something very important. You look at the tapes, that one. Can I use this hysteresis loop to find out the hysteresis method to store the information? Yes. Even nowadays also movies, when we store the movie information, the picture and the audio, video information in the magnetic tapes only. Can you see that reel they'll call, no? Can you remember? So like this brown color strip will be there. This brown color strip will be there. Brown or black or something strip will be there. Here what happened with the help of this substance, what all that audio video information will be stored, and this will be further divided into sectors. And first what happened, video will be taken. Can you remember? I think if you have some information about how that movie is, first video will be taken. Then next what happened, you can say dubbing. Shall I call dubbing? Means for all that particular video taken, what happened? During the video capture, they tell dialogues, but that will not be clearly captured. So once the after video capture gets over, video, then what we do? Then next what happened? We'll introduce audio. So in that particular tape, what happened? This particular region, this is used for to store audio. This is for video. I'll capture the video and that video will be put. Then again, they'll go for studio for each and every scene. What happened? That particular audio will be added here in sequence. It's not that easy. Again, movie also. I should not talk against much here. Lot of science is involved. Okay, I'll appreciate them. They're using science, but I should not appreciate you people watching movie because you are not watching movie is not nowhere science, no. If you make a movie, okay, good, because you are generating employment, everything. But if you're watching movie, then you are stupid. That much I can say. So the audio will be added separately. First, the video will be captured. How that information is stored? In the form of magnetic field. So this particular region again will be divided. This one. So here what happened? The scene one. Okay, they'll put some 5 sectors. So all that information will be stored here. So there's a mechanism there. So if you want, just type in Google. No, you get the overall that the way how do they introduce information, video, audio on the magnetic tape. So and what is this strip? Should be made up of magnetic material. So first it's a plastic. On that I'll give a ferromagnetic coating, and that particular areas will be there. That will get magnetized. Small areas. It's a very wonderful technique. You just read once. It'll be better watch some video or something. They'll show graphics also clearly. Okay, there's a area and memory devices to store information. Yes, I'll go for this one. And magnetic recording, this one. Just now I discussed. These are for disable for transformer. No? So like this, they can give graphics